Hi, I think this microphone is the only one working, so I'll be speaking here. If you can't see me, hopefully it's gonna deliver. Thanks for having me. Hi, my name is Sumin. Let me start with the little bio, if it's gonna. Okay. I am a KAIST alumnus. I graduated from KAIST with a bachelor and master's degree. I spent a year at Seoul Institute. During my master's in KAIST, I worked with Professor Hwasu Yeo in civil. And then I went to UC Berkeley for a PhD, and I stayed there until a postdoc. My research involves system modeling, optimization, and data science. And my research interests lie in energy, mobility, and network. And today I'm going to be talking a lot about my projects from my postdoc years. I don't think that this crowd is, I don't think I presented my work to this crowd particularly, so I hope you enjoy it. Now I was fortunate enough to get a job this year, and I started at Konkuk University this March, so it's been this semester is my second semester. And so, yeah, I'm excited to share my research. And as you see in the title page, it says do not distribute yet. Because most of my work that I'll present today, they're not published yet. So, hopefully by the time that this video gets published on YouTube, I'll have them published so that you can share them. But yeah, that's enough about me. So actually during my master's degree, that was the first time I started doing research on transportation. During my bachelor degree, I actually did water engineering. And so I started research on mobility in 2014, and I was really interested in like data science and that. But what drew me to transportation was the environmental aspect of it, like the contribution that we make to the environment through mobility. But it's really sad. It's almost been 9 years since 2014, but we still have the same mobility problems that are unsolved. It's the same thing. We're still trying to tackle these same questions. One is climate change. I think this month is a very good month to discuss these issues because climate change doesn't seem to go away. We know that transportation affects and energy sectors. They affect the climate change a lot. Also, energy crisis. I think maybe like a few years ago, this wasn't really something relevant to us, but now it's very relevant. I have a car now. Getting my car fueled up is very expensive now, right? That turbulence began like last year with the war in Ukraine and so on. So energy security is a huge issue, especially to us in Korea because we don't have gas reserve. So this kind of energy security and security issues really affect how we live and so on. So there are some mobility issues related to that. So I really like doing research with electric vehicles. Electric vehicles is not new. This technology has been with us for more than 100 years. There's been an electric vehicle since 1800s. But only now we're really embracing the benefit of EVs. And I really think that's a really good solution to both of our problems in climate change and energy crisis. Electric vehicles, where's my mouse? Okay, I hope you can see my mouse. Electric vehicles can be powered with clean and renewable energy, right? Like renewables, solar energy, wind energy, and so on. And they can emit zero emissions in their tailpipe, so they have definite advantages with climate change. And also electric vehicles, I don't think we talk about this enough. Electric vehicles have better energy efficiency than internal combustion engine vehicles. So in overall, EVs just give us a lot of tool to combat climate change and energy crises. But nothing is perfect, and we have some issues implementing those EVs in our mobility system, right? There's a new paradigm in powering those mobility. Okay. There's a new paradigm for sourcing our mobility, right? So it's a whole new system that we have to not only invent, but also modify our current system too, right? So currently with the internal combustion engine vehicles, you just go to the gas station It takes like a minute or two to fuel up and you go, right? And those systems are just so old and traditional that it's available almost everywhere. And so we take them for granted. Wherever you go, you think that if there's a road, there's going to be a gas station, and you take it for granted. But that's really not the case for EVs. You have to plan ahead your trips. It takes longer to charge. And sometimes when you go to a charging station, the charger might be broke, or somebody else might be charging. So there are some other issues that we have to consider. So with the EVs, and if we adopt more EVs, we have different goals, variables, and constraints. And I think that this gives us a new opportunity to set up a new system that actually works better than the current system of just using gas stations. As I said, this is a challenge also because we are actually integrating the mobility system to energy system. It's a whole new thing that we didn't really talk about in the conventional vehicle sense. Energy grid, where's my mouse? Okay, energy grid is like, in Korean, it's like 전력망. Energy grid is where power is generated in very large scale. It's usually operated by states, country, or cities that have huge, giant energy generators. They have a network, power generation, transmission, and distribution. And usually their operation is very rigid. It's very rigid because you have to basically use a giant machine to generate electricity. And then we're gonna use that electricity to power our EVs. And so now we're not only just changing how we charge, how we go to the charging station and so on, we're actually integrating this mobility system to a new energy system. So there is a whole lot to consider to make the system very smooth, efficient, and convenient. Also, EVs are very different when it comes to behavior. I think I'd like to think about this system in two different groups, private individuals and fleets. And when I say fleets, I mean like logistic fleets like Coupang or Amazon or something like that, like an operator having multiple vehicles in their company and operating them. Their behavior is very different because individuals in the States, it's more the case that everyone really has a charger at home. Like they have their own garage, they park and they charge. But it's not the case for Korea, right? And in the apartments, there's like maybe like a couple of chargers and you have to usually share them. They might be broken. So there's a lot of issues that influence the behavior, people's behavior in charging. Do you want to charge at home? Do you want to charge at the 휴게소, like the what's 휴게소 in English? Rest areas on the highways. And so there's a lot of decisions that people consider a lot more just because it's EV, right? Ooh. So, but then we want to take this challenge as an opportunity as an engineer, right? So we want to integrate these two systems the best way so we can reap the best benefit out of this too. And so I think in my personal opinion, the key approach to do this is to use those connecting infrastructures that is available that connects between the energy grid and EVs. For us to optimally integrate them, we have to consider all these systems that's going to enable the flexibility, reliability, efficiency, and convenience of charging and energy operation. These are some examples of those connecting infrastructure, road network, charging points, and parking points. But they're and they look very tangible. They're tangible infrastructure, but I also consider intangible infrastructure as well, like algorithms and softwares and data, right? So hopefully, it's a very long introduction. I like laying the road before the presentation starts, but basically this is what I usually focus on, the connecting infrastructure and how to make a system better so that we enjoy the environmental benefits of this system integration. Very long intro. Let me sip some water. Oof, how long do I have until 5? 5:30, okay. Okay. So I did prepare 4 topics, very ambitious, I know, but I'm probably gonna go through the first 3 only, and then probably gonna refer you to a paper for the 4th one. Out of the first 3, I would say the 3rd one is my main project that I did with like the biggest passion. The first one, vehicle grid integration, is probably one of the classical topic in integrating vehicle to the grid, very classical. I'm gonna go very quick with this. I did that project. That's my first project as a PhD when I arrived at UC Berkeley. That was the first one that funded me. And the second one and the third one, they're actually funded by the same project. And the second one is quite new in topic. I think it's gonna be really kind of fun to go over it, but I'm gonna go short with that. The third one I'll go very deep into, I think. Okay, hopefully I'm gonna have enough time. So, okay. In California, which is very sunny, where I lived for 6 years. I was very happy there. In California, we have some issues. California is super rich, I think. And so they have a lot of EVs. When you go to Silicon Valley or San Francisco, Tesla is everywhere. A lot of people they get tax subsidies as well, so a lot of EVs are there. But there are some issues with the EVs. So if you look at this one, this graph is called like it has something called duck curve issue. It's supposed to be like a duck, like quack, quack, and it's like a duck. And so the yellow curve shows the electricity demand of Northern California. If you look, it's a megawatts. It's a 전력 demand죠, 전력 수요. Power demand of megawatts. This is Northern California demand. And in California, in sunny California, we have a lot of solar energy generated in the state level. We have a lot of solar panels in the state level. And the green curve shows the renewables that increases super sharp in the morning when the sun comes up. And then it goes relatively pretty stable. And then it drops when the sun goes down. And the increase and decrease here is very abrupt. It's very, very quick. But then that's good, right? Because we have a lot of renewable energy, and you would think, oh yeah, this is perfect. Let's use this energy. But no, that's not really what happens in reality. What happens in reality is the red curve. The red curve is the net demand, which is roughly demand minus the renewables. But and you might think, okay, but we decreased this amount of energy to produce. Isn't that good? That is really good, except for this evening ramp part, where the net demand increases so sharply. And not only is it a problem because of this high peak, but it's also a problem because of this sharp increase, the ramp. It's called evening ramp, and this ramp power goes to approximately 15,000 megawatts only per hour. This is a problem because usually in the power generation, it costs a lot to turn on the power generator. And it also usually, you have to use some dirty energy sources like coal or natural gas so that you can output that sharp increase. You can't really do that with a lot of renewable energy sources. So this evening ramp is a big problem in California. But what is worse is that's when people charge. People come home from work and then they plug in the vehicle, and that's when people park most of the vehicles, right? And so we expect as EVs increase in population, this ramp is gonna get even worse. So we pose vehicle grid integration as a solution. VGI, or vehicle grid integration, is defined like this: altering the time. Oh, where's my mouse? I'm looking for my mouse. Okay. Time, power, and location of charging of EVs so that we can make the energy grid operation a bit better. And I've written out some evidence, these 3 little bubbles, that shows how we can do it. The 3 little bubbles are actually real concrete information that I extracted from the BMW vehicle set. I analyzed that the vehicles are parked most of the time. A lot of the vehicles, where's your vehicle, professor? Is parked. My vehicle is parked. Most of the vehicles are parked 95% of their lifetime, right? And people usually charge their EVs only once every 5 trips, right? They don't charge all the time. They don't have to because they have enough range. And every time they charge, they only charge about 4 hours. So this gives us an idea of the flexibility that we have with the EVs. We have so much to control because they're basically sitting idle. So this is probably the biggest motivation for vehicle grid integration. We have room to control. And so for my first project at Berkeley, we wanted to study how much is that benefit in controlling the EV charging so that energy grid can live a little better, right? So at the time, I'm not sure now, but at the time, no study actually investigated the real potential of VGI with actual EVs. Is this gonna go onto YouTube, right? Because there's a fun story behind like the funding source, but maybe later. After this project, I'll kind of share like why BMW started to fund this project. It's a funny story. But anyways, BMW North America was, it funded us to study the benefit of VGI in Northern California, and PG&E, the second one, is the Energy Grid Company of North California. Sorry. And then the Energy Commission funded our project. Okay. And for more rich detail, refer to this BMW Charge Forward report that you can Google on. There's going to be a good little PDF file that comes up. So we were very fortunate to have in our data 250 electric vehicles, like BMW electric vehicles in the San Francisco Bay Area, and we were able to study what the benefit would be. I'm not going to go into detail about the modeling, but basically we formulated an optimization problem to change their charging schedule to see how much better energy grid was going to be like. Okay. This graph and the next graph kind of shows the basic idea of the optimization. So for example, if you look at the gray line here, this axis is LMP price. So that's basically the price of the grid operation, how much it costs to generate the electricity. And let's say that the red curve is people just charging whenever they want, wherever they want, right? So I want to go here. So let's say the vehicle is here, it arrives at location 1, and it charges this much, it travels, arrives at the second location, and it doesn't really charge, just because this person doesn't want to charge here. Let's say that this is business as usual, but unfortunately, it might coincide with the time that it is very expensive to generate the electricity, which is actually the case because in the afternoon, it's more expensive to generate the electricity in the afternoon. So our idea is to shift the charging schedule to when it is cheaper and cleaner to generate the electricity. And by doing that, we not only shift the time of charging, but we also shift the location of the charging. So we wanted to see how much it can benefit the energy grid. And I'm going to skip the sample here. And this is our result. This is the maximum potential we expect from controlling them. The percentages are huge. This is huge result. The energy grid can benefit from controlling the EV charging. They can save cost by 37%, increase the renewable mixture in EV charging energy by almost half, and marginal emissions can be reduced by 30%. So there's huge potential in controlling EVs is what we found. And basically, the intuition that we get from this result is not just numbers. It's how we would do it. So we analyze the results and we realize we often shift the charging that happens in the afternoon to during the day. And where are the people during the day? Workplace. So it kind of gives us, workplace, usually, in shopping or in workplace. somewhere outside. So it kind of also gives you like a evidence to support your policy, right? You want to push forward in installing more chargers in the workplace and in the shopping malls and so on. So This one was a fun exercise for this. I really want to explore this kind of topic in Korea, but unfortunately in Korea, renewables is very marginal in the energy generation currently. And for some reason, people just use energy very consistently 24/7. I have no idea why. There's like no pattern. People don't go to sleep or something. So I really want to explore how we can use VGI in Korea specifically. So reach out to me if you have any ideas on that. I'll be very interested. Okay. I think we're good in time. That was the first topic. The second topic is very different. I think it's very different. I like this topic, but I'm gonna go very quickly on this. Automated parking and charging. Before I go to the second topic, I think I just wanna shout out parking doesn't get enough credit in terms of research. When it comes to self-driving cars, autonomous vehicles, they do have to advance a lot on the road to drive safely and so on. But people don't really talk about how how the self-driving cars should behave in the parking lot as much, right? So in this topic, we talk about not only the automated parking, but also automated EV charging. So this one is really fun, I think. As I said, the behavior of charging is very different. The sourcing of the EV, sourcing of mobility is very different, right? From internal combustion engines to EVs. And this behavior is kind of new to us. So I think we have some similar global challenges as we face this like rise in EVs. So these are two examples. The left figure shows like this little sign that I got from Europe. It says electric vehicle parking only while charging. So people are angry because EVs that are done charging or even like internal combustion engines, they just sit in the charging spots so that other vehicles can't charge. It's something very similar. This is from Daejeon itself, right? And it says they're gonna give a ticket to vehicles that occupy the charging spots and so on. This happens because we don't have enough chargers. We don't have enough chargers. It takes longer to charge. The problem arises from the shared use of EV chargers. In our group, we called it overstay problem EVs, so that EVs, after finishing to charge, they just stay there. So then the infrastructure utilization just kind of goes down. Because we're engineers, we want to create like a really fancy solution to this shared use problem. So let's say, okay, let's automate parking. Let's automate charging and parking. Then we can think about, oh, okay, if you're gonna achieve that, how are we going to facilitate those self-driving vehicles? Are we gonna just let them do what they want each and individually, or are we gonna do like a central way to control the assignment and the charging and so on? So that's basically the motivation for this second project. We want to minimize a collective objective, for example, parking time, and maximize some charging infrastructure in a charging and parking infrastructure. We're not only going to allocate the vehicles to parking spots, but we're going to also schedule when and where they're going to charge. And on top of that, because it's autonomous vehicles, we're going to do optimal control of the self-driving cars within the parking lots. So for this project, we had really fun data here. This is an actual parking lot, people driving, so this is just human driving. And so we took this as a baseline case of human behavior. And on top of that, we simulated some fun things to compare how our algorithm works. Okay. Okay. So on top of that baseline, we could design a new system for automated and parking and charging control. This is not very. This is not like it's not like a shockingly new system to think about. It's a cyber-physical system where we have a cloud server, and I have to go there. Okay, we have a cloud server that collects information from charging a parking space and the charging space. We would have physical parking space, and we would have physical charging space, and we would just collect data from it, feed it to the cloud server, do some algorithms to allocate parking and charging spots to vehicles and then distribute it back up. So it's a pretty standard framework for cyber physical control, I think. But our contribution for this paper was actually not only that cyber physical framework, but also the simulation framework. Yeah, so I think we would be bridging a gap between single vehicle control for automated vehicles and an infrastructural control framework. So in this framework, we would simulate multiple vehicles in the parking lot. Sorry, I have to keep moving back and forth. We have multiple vehicles in the simulation. We would generate the vehicles, and we would have some sort of control strategy to assign them to parking spaces and charging spaces. And for each individual on the simulation environment, they would go through single vehicle planning and control so that the self-driving cars maneuver on the parking and charging, and so on. So this framework, for it to work, that was our contribution development of this simulation framework. Okay. And what we found was actually quite intuitive. Two things we found. On the left shows automated parking saves time. Let me play this video. So if you look, the gray vehicles, oh, it's lagging. Can you see? Ooh, it's lagging a little bit. Please. I don't know if you can see it. No, it's not working. Oh, there you go. So the gray, no, it's not working. Okay, it's okay. The gray vehicles kind of show the shadow of human drivers that we saw from the data set. And then the colored ones show the automated vehicles. And you know, in a parking lot, let's say that you go to like a huge parking lot with a lot of vehicles, how do you drive? You usually drive very cautiously, right? There's people walking around and stuff, and you don't know where you are. You want to look for parking spots, and so you drive super cautiously, and that takes a lot of time, and it causes delay, right? So when we automate those vehicles, it actually saves a lot of time because they know where to go, and so they efficiently execute the maneuver and parking, right? So it saves a lot of time, hence saving energy. Also on the right, it shows that automated charging improves utilization. Fingers crossed it's gonna work. Okay, so see slots on the right top, it shows charging spots. So we can schedule so that the vehicles that finish charging can move out of the charging spots so that other vehicles can go ahead and charge. So they're basically swapping, oh, this one video's finished, but when they're done charging, they're going to move out so that other vehicles will go and charge so that we can maximize the infrastructure utilization. Next one. Okay, and so this simple idea, I think, automating parking and charging got us a US patent this year, so it's very happy with this patent. So if you have any citation that you want to look for, this is one, please cite my paper. So I think that was a really fun topic. I don't know. Parking and charging, I think parking is very often overlooked. So I think that one was a really fun research. A paper to be published very soon. Okay. Can I take 5? Can I take a 5? Or break or questions or something? Yeah, I don't know. I like to take a 5-minute break from time to time because your focus kind of goes, and then I go. So if you have any questions, give me any questions. Let's take a break for 5 minutes. Quick 5. Right? If you have any questions, 괜찮아요?
Have you ever taken or looked at the idea that automated parking and charging, not inside of a parking lot, but like for example, like making parking lot and charging station in very expensive land area building, then we can see that if the car is autonomous car, then this car can't just drop me.
Yeah.
Then like that heading to charging a parking lot which is located far away
somewhere else.
in
Yeah.
area
Yep.
that we can like maximize
Oh yeah, yeah.
this kind of
맞아, 맞아.
like so have you ever
I definitely thought of that scenario where the vehicles can actually drop me anywhere, and then that means that we can save the rent for parking, right? And then it's gonna be a lot more efficient and so on. And so my answer is yes. We've thought about it. That project particularly was we had a clear goal, like we had a deliverable for the project, which was to actually show it in the field. So we couldn't like show the self-driving cars outside like a premise. So we had to define like a premise for us to do experiments, and that's why we had a confined zone of the parking lot. But that also means in this scenario, in the second project, that means that those kind of technologies can be implemented way faster than the futuristic case where vehicles drop you off, right? Because if you think about it, if you isolate that parking lot to only autonomous vehicles, that means it's more safe because people don't need to really go into the parking lot. Yeah, so there's a lot of layers to enable various autonomous vehicle technologies, but definitely, yeah. But that concept goes well with the shared mobility concept too, right? A lot of shared. Yeah, 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 yeah. So actually, a very fun project was how to design a parking lot when the vehicles just drop you off wherever, because people don't have to open the door. So each parking dimension can shrink. So instead of the door, the length of the dimension of the parking lot is going to be very tight, so that you don't have to open the door. So then you can compress the parking lot dimension, right? So that was a huh? 문콕, 문콕, 문콕. Yeah. No 문콕. Okay. Okay. Well, I gave you a 5 to take a break, but I guess you're very enthusiastic. Okay, third topic. Hopefully, this one is super fun. I'm writing this paper currently, probably gonna submit it very soon. I'm very excited for this project. I think people ask me because I just recently got a job, like, oh, what's your interest? What's your research interest? And I think I'm really interested in logistics and 항만이 뭐죠? 항만? Like international logistics even with the ships and the planes and stuff. I think I'm interested in logistics. Oh. Maritime, yeah, maritime logistics. I think I'm very interested in logistics that way. Because I think, yes, self-driving cars, very cool, very fun for passenger vehicles, but I think like a really big influence that mobility can have comes from the industry. Because there's a lot of vehicles that we don't really think about are used for logistics, and I think if we do some, make some innovations in logistics, we're gonna see the benefits very quickly. Also, they have the capital, so I think logistics is something that I'm currently very interested in, and this project is my last project at UC Berkeley, and that's probably why I'm still very related to this, and I feel very close to this topic. There's a lot of movement in electrifying logistics. I think before I went to the US, there weren't a lot of EV trucks. But now I arrived this year, and every truck is electric, and every little car for post office, 우체국, they're all electric. Everyone's all electric, I think, because of the heavy subsidy for electric vehicles for logistics, right? I saw that similar change in the US before coming. Amazon, they created their own custom EV trucks by Rivian, right? And so this was this was driving around town in Berkeley by the time I was leaving it. Electric vehicles is awesome. They create like no emission around. It's very pleasant to be around EVs and so on. They have the benefits that I talked about before. But if you are to use those vehicles for logistics, you have some challenges. Limited range, right? So Mercedes-Benz Amazon truck drives up to maybe 450 miles, but the electric van, a third of that. And also it takes longer to charge, as we discussed, in the charging infrastructure limited. So that gives you a lot of more, decision variables and constraints to think about when you want to optimize your operation, right? Taking a step a little back and maybe adjacent, a tangent a little bit, is I want to discuss why I started doing this project, a little bit of background information. So we looked at electric vehicle logistics, but I want to explain why we came up to do this. So this project is phase 2 of something called ARPA-E Next Car project. This one was funded by Department of Energy in the US. In the phase 1, its goal was to reduce energy consumption by 20%. So, but okay, 20%, how does that sound to you? If someone gives you a lot of money and say, okay, save energy by 20%, it's almost impossible. 20% is not something that we have achieved so far in history of internal combustion engine vehicles. Internal combustion engine vehicle efficiency hasn't been dropped for almost a century. So for us to reduce the energy consumption by 20%, that technology is very innovative, right? But with the autonomous vehicles, we can. And so in phase 1, they did something called eco-driving, which is talking to the signalized intersections, and then driving through signalized intersections, smoothing out their acceleration profile. They were able to show 20% savings, right? And so ARPA-E was like, amazing. So we're gonna give you another project. So that's the background information of project 2, the phase 2 of this project. And they upped the percentage to 30%. So by the time we started the second project, we were like, okay, how are we going to save 30% energy consumption? And so instead of looking only the actuators of self-driving cars, we had to broaden our scope of energy consumption. Thankfully, they didn't define how, so we could use any type of technology we had in mind. And actually, the parking paper, the one that I just discussed before, it's also a part of this project. So in this project, we approached this problem in many facets of driving. So not only did we discuss the actuator control, but also the parking. And then this one is us just really trying to achieve that 30%, which is going even broader. We're going not just vehicle sense, but in a fleet sense, in a network sense, on saving the energy consumption. So that's why I just want to motivate how we came to this project. So in here, we want to solve the EV fleet routing problem so that we reduce the energy consumption by 30%. One key thing about this project was that we had to actually show, in the field, that it saves 30%. So that was really tricky, but in the end, we got it. So very excited to share it with you. So this is the basic framework of what we did. At first, we would have some sort of scenario. So I think a really good example of this scenario, where's my mouse? Okay, this scenario is like a Coupang, right? I'm a Coupang hub operator. I have a lot of trucks, and I have some customers in my network that I have to visit today. So this will be this graph. Sorry, let me just grab this. This would be visualizing all the customers that I have to visit today. And then I would have some sort of fleet, like a Coupang truck, like a set of Coupang trucks here. And from this network, I would make a digital representation of the network. And so we worked with the startup called WhiteSense that estimates the energy consumption on a path. And this path, this energy consumption will be estimated based on a lot of driving data they have. And it doesn't include not only the distance, but also the slope of the road, weather, weather as in HVAC consumption and so on. And they considered when you're doing a right turn, you would have to stop and go and stop and go. They also have a lot of data on traffic congestion, like a link-based link-based traffic congestion to how many stop and goes they would have. So they have extensive vehicle data, and so they would have some high precision energy consumption estimation. So we were able to actually use their API very thankfully. And we will create like a network matrix that represents the traffic network, not only in terms of travel time, but also energy consumption and distance. A really fun thing about this digital network that I'm not showing here is that we had that matrix information for every hour of the day. Because, you know, during the morning, there's going to be a morning peak, and then in the afternoon, there's going to be another traffic behavior, right? So we would generate this information for each hour of the day. I'm not going to go through the details of this solver, but we somehow solve this problem via meta-heuristic method, which is an approximation solution method. Basically, that solves a huge optimization problem very fast. If you're interested, I can share a lot of information on this. And then output is the routing solution and charging solution. And the routing solution includes for each vehicle, okay, you're going to go to this set of customers in what order, right? So that's a routing solution and charging solution. We created this framework hoping that it's going to save energy by 30%. Yeah. Okay. And we work with Hyundai. They actually gave us a vehicle to test, Ioniq 5, which is a battery electric vehicles. And we compared two cases, energy consumption minimizing routes and travel time minimizing routes. And we took the travel time minimizing route as our baseline. And we wanted to see if the energy minimizing routes reduces the energy by 30%. Actually, I drove that vehicle a lot, all the time. Successful was our experiment. We were able to show from the field that we save energy up to 31% in the off-peak traffic and 23% in the peak traffic. And at this point, I want to say hooray, because this one was something that we really waited for. It was a result of a very careful experiment design. So I don't know, you know Berkeley, but this is Berkeley area in California. This is Trader Joe's. This is Costco, and this is Berkeley Bowl. These are like 3 supermarkets. And I chose to do supermarkets because they have a parking lot that I can stay at. But these 2 graphs show the samples of the experiments. And on the left is the travel time minimizing route, which is the baseline. And this is the energy minimizing route, which is, our proposed algorithm. You can see that here, we want to traverse these 3 supermarkets. And this red path, do you know what this red path is? This is highway. This is highway, and then this is not a highway, right? So you drive around like 100 to 110 kilometers per hour on this highway. Whereas in here, we have signals, right? I think it was 35 miles per hour, which is like 60 kilometers per hour, right? So the routing solution of the baseline tells you, okay, if you take the freeway, it's faster. This is our baseline. But if you want to minimize energy, okay, you can take the freeway here, but on the way back, you're better off using this arterial road, right? And then because you're driving slowly, your energy efficiency is better at a speed around 60 kilometers per hour than going at like 100. Also, this distance is shorter, right? This is more direct path than going all around it. So not only do you save distance, you also save energy. And that was a stark difference of 31%. Also, the speed profile shows you like very clearly how the blue is the energy minimal route. Oof, it's lagging a lot. The blue is the energy minimal route, and the red is the time minimal, the baseline. You can see that they actually drive longer, right? They drive further distance, and then they usually stay at a high speed, like 100 kilometers per hour. Whereas in the blue, you can see that they stay around 50 a lot more. So that's essentially how you save energy in logistics. Right? We wanted to take that result a little further and did a lot of simulation tests. We tested various cases like battery EVs, like the pure EVs, and plug-in hybrid EVs that have both engine and the motors, and wanted to see what other corners of operation we can save energy consumption on. I think Professor Lee, you definitely know this topic very well because it goes very directly to how we should plan the infrastructure in our network. So on the left is showing, they're both showing energy minimizing solutions. But on the left, we assume that there's no charging. There's no charging. And on the right, there's going to be a charging here, right? I also think that this is not very often discussed. If you have good enough infrastructure, it can save you energy. Other times they usually talk about like saving costs, saving time, and so on. But it can also save energy, right? Which aligns so well with our environmental goals. So if you look on the left, I'm probably going to go here. If you look on the left, if you have no charging, because electric vehicles can drive only short distance, you have to dispatch 2 vehicles, right? But on the right, because there's a charger, the vehicle drives down, charge, and extend their range, and then drive back up. And what ends up happening is reducing the deadheading miles. And then, so what results is the reduction of the total travel distance and energy consumption, in theory. Okay. This is the last result that I'm gonna talk about. I think it's a good timing. Last simulation test is this graph. We wanted to see what's gonna happen when we relax the time constraint of the operation. And time constraint, namely, we took the time constraint as a driver shift. Like how many hours can each vehicle drive for, right? We wanted to see how it affects the energy consumption, right? Before discussing further into this topic, I wanna talk about what it means to us, right? What does it mean for us to extend the driver shift from 0 to 24? What does it mean to you? Does it give you any like insights? No? Yes. Yeah. So it's like, okay, right now we have vehicles, maybe drivers, they work maybe 5 to 8 hours, right? So they're working around this region, right? And everyone talks about, oh, autonomous vehicles, it's gonna give us a lot of benefits, right? And so, okay, let's relax the time constraint of each driver to 24 hours, which means autonomous drivers. But what ends up happening is that for this specific dispatching scenario, yes, as we increase the driver shift, energy saving, we definitely see some energy saving. But past a certain point, the marginal return kind of goes down, right? There's so much you can save by relaxing the time constraint. I mean, obviously this result is only for that city scale, very small network. And I'm pretty sure this graph will look very differently when the network is much larger, right? Like long haul networks and so on. But this kind of gives you an idea, okay, when we want to deploy our autonomous vehicles for logistics, we have to think about at which specific scenario they must be deployed for so that we make our money worth for the autonomous vehicles, right? Yes, I think this is a really, I think this graph was very interesting, connecting it to autonomous vehicles is what I was saying. Okay. Actually, that was a little bit anticlimactic, but that was the end of the result. I want to point out the main contribution of the last paper was that it's super interesting what we're doing in terms of mobility research when we talk about autonomous vehicles and like how they can shape the world and everything. But with this research, I learned so much that there's this huge gap in our system that they were developing to how they can actually work in real life. So when I was driving the vehicles and I drove that little Hyundai Ioniq like 30 times to create the samples, I drove all the samples. And there was so much randomness in California, and people drive very differently in California than here. So for example, I was driving and this truck just blocks me in front of the lane and doesn't leave for like 5 minutes. So I was stuck before the truck for like 5 minutes, messing up the entire route. Sometimes there was a train path in Berkeley. It stopped me for like 3 whole minutes. What else? A lot of road work, unexpected traffic congestion. It happens all the time, right? You think that you can get to work in 5 minutes, and then you end up taking like 30 minutes. And actually, in one of the samples, one day there was like a huge traffic congestion, and then it was like really hot. So I turned on the AC because I had to survive. And then it ended up actually consuming more energy because HVAC energy is serious. So, and then from that experience, I learned, okay, there's going to be some theoretical optimal level we want to reach, and we strive to do that. But we do want to make the system very robust to all of the uncertainties in real life, and we have to consider all the practical applications. One another story that I want to leave you with is that when we were creating this system, we had to actually talk to a lot of the investors for this technology. This project was not only about like creating this technology, but also like selling this technology to real like investors. And so our collaborator, they reached out to like UPS, FedEx, USPS, and even public transit agencies. And we learned that they really need this because they're super conservative with the EVs. So for example, one public transit agency, they have this huge electric buses, but they were operating the buses only between 50 to 80% SOC because they were very scared that it's gonna drop below like 20 and get stuck in the middle of nowhere. And that's real because electric buses, they consume different energy depending on how many people they're carrying and like a lot of HVAC and so on. And so when we're actually adopting these kind of technologies to real life, we have to consider those factors. And so I don't know, this project was super interesting to me because it kind of broke me out of my shell thinking, okay, I thought I was creating this super fancy thing, but for it to work, we have to really get closer to the practical applications in the real life, and we have to be very aware of how they can be used in real life. And so, yeah, I'll leave you, I think the time is very good to end here. It's like 4:55. Thank you so much for listening. For the last project, you can just Google me on Google Scholar, and then there's gonna be this is the most recent publication you can look. I'm not gonna have time for this one, but yeah. If you have any questions, I think there's my email on the last slide. And so thank you very much. Yeah, thank you. If you have any questions, let me know.
We want to finish at 5 like sharply.
Okay.
So I think we have time for Q&A.
Questions?
Yeah, so
안녕하세요.
Chemistry, and also from Yonghwa's History Lab. I'm from the AIX module and CEE too. And your project is really interesting, especially I'm really high interested in electric vehicles, so we are some common. I also think about the EVs parking, but right now what I think is like more current situation, not the autonomous vehicle, but how the people can actually make the EVs charging parking can used by many people, and people can like automatically tracking how the EV charging is empty, available, and then how if it's already done, the other can use something like that, more robust that can use it.
Yeah.
One thing I want to question, when you use the Ioniq 5 for the testing in California or something, Berkeley, I just want to know, do you use some mode?
Oh yeah, for sure, yeah.
The mode.
You mean regenerative braking mode?
Yeah, the passenger or something, because like there's like a 3 modes, so normal, sport, and eco. And then like
Yeah.
several features also that will affect the
Yeah.
efficiency.
Yeah.
I just want to know about that. Like,
Yeah.
How can you achieve the 30% itself?
Oh, okay. The question was usually I don't know if you've driven like an EV. Usually a lot of yes.
I will.
You will, okay. A lot of EVs, most of the EVs come with like driving modes that the users can switch between like full regenerative braking mode and like no regenerative braking. So EVs, they have motors which behaves very different to engines, and so in theory, if you just use the pure energy efficient mode, when you step off the pedal, it goes immediately to regenerative braking mode. And so the vehicle will jerk, and then it's gonna start to absorb that kinetic energy back to charging the battery. In my experiment, I kept it at I think level 2, which is very similar to the conventional vehicles, because when I was driving. So I was very new to EVs, and when I used the full regenerative braking mode, I kept getting car sick because I couldn't control it. I was driving, I couldn't really drive very nicely, and I had to drive like hours a day. So I used like a regenerative braking mode too, but that setting was the same all throughout the samples, and the HVAC mode, it was also consistent. And actually, I don't know if you saw, but the vehicle actually had a bit of a horn. I don't know if you saw. Because that vehicle was used for other autonomous features of the same project. Yeah, so if you can see, it's got like little horns on it with the LiDAR sensors and everything. So that increase of surface area definitely changes the energy consumption. But one thing, we just did one thing the same setting for all samples. And the 30% saving was saving of energy minimizing routes compared to the travel time minimizing route. So that was our baseline, not like different vehicle features or anything like that.
Another question: Is there any like trade-off?
Trade-off?
Yeah.
Time.
Like, when you increasing the energy consumption,
Mhm.
is it also like decreasing the driving satisfaction? The driving very
Not much driving satisfaction, but time is definitely a trade-off. I think I didn't really highlight it, I guess. But you save energy if you drive at a efficient speed range. So the trade-off is time. It takes a bit longer time and to save energy. Yeah. Mm-hmm. Anything else? 먼저. 한국말로 하셔도 돼요. 한국말로 하셔도 됩니다.
네 번째 연구에서 패스를 계획하는 위해서
네.
생각보다 엄청 많은 디스터번스가 있을 텐데
네.
특히 테스트한 날짜를 보면 9월이잖아요.
네.
예를 들어 추운 겨울이 되면 HVAC 시스템의 에너지 컨섬션이 훨씬 많아지고 이런 것들에 대해서는 예를 들어 결론은 계절이 달라지거나 디스터번스가 엄청 생기는데
네.
그걸 어떻게
일단 제가 그다음에 뭐라 해야 되나? Okay, so the question was like, what was the impact of HVAC with the different weather on the path, right? So I didn't really say it in detail, but this energy consumption estimation, it considers weather, right? And this path, so I would give YSense location 1 and 2, like origin and destination. And then they use the Here API. Here API actually, it's kind of like Google navigation system. So this path is generated by Here API because you want to actually use a path that people drive, right? You don't want to go like in like a very crazy path just so that it saves energy. You want to use like practical navigation route. So we would extract the path from Here API, consider the weather, what day it is, what time it is, what the temperature is like, and what the traffic congestion is going to be, and then have the estimate. So what is very important is to have that information. So if you have that information, your routing will be good. So if you don't have that information, not so good. And actually, when I was testing, I said like there was an unusually hot day. It was like one day it was super hot, and the traffic congestion was unexpected, and I was stuck in traffic for like many minutes, and I was really hot, and that's when I turned on the AC and then consumed a lot of energy. So definitely we do have to plan for those events. But in general, I don't really show it in the results. In general, if your travel distance is super long, like 100 kilometers or something, that kind of effect kind of evens out. 그 주행 거리가 좀 길어지면 그런 에러들이 조금 그 average 되면서 좀 나아지는 경향이 있고, 그리고 네, 그래서 전체적으로 overall 봤을 때는 리절트가 나쁘지 않게 나올 수 있어요. question 있었는데. 네.
First of all, thank you for your nice lecture. I have a question in the Berkeley project. I was curious about how did you get the amount of energy consumption? How did you get that?
Oh yeah, so we installed a device called iPetronic that collects the battery voltage and current, and so we calculated the energy from like the actual battery output.
So the energy amount per road, every road is in the data.
Yeah, so voltage and current was constantly measured. I think it was like 0.1 hertz, so almost continuous in the entire sample. Actually, it also collects HVAC power consumption separate to the driving consumption, so that's how I could separate the AC energy to driving energy. And then on that hot day, I actually separated the HVAC, and when I separated the HVAC, the route was more energy efficient, but because of the HVAC, the energy consumption was actually worse. Yeah. So, a lot of information. That's one of the benefits of EVs, because it digitalized a lot of information that we couldn't really do with the ICE vehicles. With the ICE vehicles, energy measurement is very difficult. Usually you do with the weights. You know, like the trucks, they weigh the trucks so that they weigh the fuel in the tank. And that's how you usually measure energy. And because it's fluid, it's very difficult to measure how much fuel you have left in your car. But with the batteries, with the electric vehicles, most of the information is digitized, and then you can even upload them. I think a lot of OEMs now have their apps, right? Telling you, oh, your vehicle has how much energy left and stuff. So all that information is very available to us. So a lot of room for control, for sure.
Thank you for the presentation. In the post research that we
VGI? Yeah.
I think to reschedule for the new vehicles charging location,
Mhm.
I think it will take lots of people.
If I what?
I think it will take lots of people.
Yeah.
And
Yeah.
there are really important factors like the charging prices.
Oh yeah.
So I want to know about the details of the optimization, the decision variables.
So in this project, our goal was to estimate the maximum potential, and we were very lucky to have all the information we needed, including the energy price and the location of the vehicles and so on. Energy price, I think when you work with Energy Grid, it's pretty okay to get. You know, it's quite accessible. But where people are and when, like, what their schedule is like is almost impossible to get. Like, how will you know each vehicle is available for you to charge and stuff? Because it invades a lot of their privacy. So parallel to this project was another project by BMW. So BMW being a very fancy car, they have apps. And they asked for the EVs. And they usually, they were studying the impact of pinging, like sending an alert on their app saying like, oh, a lot of renewable energy generation. If you charge now, we'll give you $1 or something like that. So on the bottom, I didn't mention, but for the future work, there's driver incentives and compliance. Huge issue to really get the benefit. And the reason why I kept saying maximum potential is probably because of those issues that hinder us to really get to that level. But driver compliance and incentives is definitely a huge effort. Like, yeah, actually, I didn't even include this slide in this slide, but there's a lot of pricing strategies for you to incentivize the drivers to charge a certain way. Very interesting topic. 답이 됐나요?
예.
Yeah, go ahead.
And you developed with a very large scale.
Hmm?
Very large scale.
Large scale, yeah. Yeah.
I want to know some difficulties. What is the difficulties in large scale?
The optimization itself was not very difficult because we formulated the problem to be convex. I don't know if you know, but convex optimization is quite quick to solve, so it wasn't a big deal. But what we didn't model is the impact of EV shifting behavior back to the grid. So there's some feedback relationship. Right? There's some feedback relationship because the supply of electricity is shaped that way, so you want to shape the demand this way. And then if you change the demand, then again, you have to adjust that supply to reflect that demand. So there is some sort of feedback relationship, but we didn't really model it here. Yeah, but I think people are investigating that for sure. Yeah. Questions? 교수님.
Dr. Wu, I really enjoyed your talk
감사합니다.
because you are dealing with the three big words: sustainability, energy, mobility. I think only one word is enough, but you are dealing with the three. And I love your powerful voice.
Oh, thank you.
And, sometimes was persuasive. I hope you will continue.
Thank you.
I have a couple of questions if you allow me to.
Yeah, sure.
You thought actually back to the second question about weather.
Mm-hmm.
I think your frame of currently dealing with, I guess, the California weather.
Perfect.
So,
Perfect sunny weather.
yeah, exactly. But sooner or later, you may modify your
Yeah.
model considering those areas, 4 seasons, or cold weather, etc. But at this moment, I guess you are dealing with
Yeah.
almost monotonous
Yeah,
weather.
for sure. Yeah.
So I hope that will help the question to the second question.
Mm-hmm.
Now my question, pertinent question, personally, I'm interested in, you said that the third topic, a very fantastic topic, eco EV fleet discussion. You said you estimate energy consumption based on AI, but I did not hear the details because of time limit.
Yeah.
Could you elaborate a bit about?
Okay. Yeah, sure. So, that project was like a collaboration with a startup company that specializes in the AI of an energy estimation. But what I know basically is that they have a lot of vehicles out in LA, in Chicago, New York, driving around collecting the information on the energy consumption of the EVs. And they have actuator information like acceleration, weather, slope, and everything. So they do a mysterious model of learning, like a black box, mysterious, very, very fancy and mysterious, that where you input all that information like slope, weather, and so on, and outputs the energy consumption. That black box is their secret sauce because it's a startup. So I can't really disclose too much, but basically they have extensive data sets on the energy consumption, vehicle control, the network like grade, road grade, and the stop and go and all that. So yeah.
Yeah, so you can see the lots of variables,
Yeah.
and then you probably build kind of big data
Yeah,
for that.
for sure. Yeah.
That makes sense.
Yeah.
Sometime I want to talk to you more. about
Yeah,
it.
sure.
But I think I was very fascinating what you are doing. I hope you will continue.
Yeah, thank you
And
very
also, I
much.
have one minor question. You concentrate on electrical vehicle, EV,
Yeah,
on
yeah.
the study.
Mm-hmm.
But myself in United States, I'm driving the hybrid.
Yeah, yeah.
So you do not consider
I-
hybrid.
Oh,
Or, and also, like when you go to charging station, I notice sometimes there are trees.
yeah, oh yeah.
There's a
Yeah,
tree.
for sure.
Do you
Yeah, yeah.
consider those things, or in the future you will consider?
So actually in that project, I didn't show, we did have a hybrid vehicle for testing. We did. The reason why I didn't experiment with that was because it was so difficult to measure energy consumption for the fuel part. It's just because the experiment was hard for me, because I was the only one doing the experiment. I didn't want to measure the fuel, and so I'm sorry. But PHEV was definitely, it's actually in the paper, so if I publish the paper, I'll share it with you. I'll just share one really fun insight with you though. For the simulation, I tried mixing PHEVs and just pure EVs, right? The benefit of, you probably chose hybrid vehicle because it has longer range, it's more reliable and so on. But its efficiency is not as good as EVs, right? Because it has both motor and engine is less efficient. The funny thing that I found in the results that I didn't really show today was that you actually end up using battery EVs more than hybrids. If you want to save energy, you will just use battery EVs to the maximum, and then for the little bit that you cannot achieve with the battery, you're going to use hybrid. But that's ironic, right? Because you got the hybrid because you can drive longer distances, and you end up not using them whenever you can, if you want to save energy. So there's this irony. And that led me to the study on the infrastructure, because that's the point I wanted to make. If you have right infrastructure in the right location, you don't need hybrid. You just use your EV and then save a lot of energy there.
I think at this stage, you did the right thing. You can use the pure EV. Okay?
Yeah.
But in the future, maybe you can, add more modified variables.
Yeah.
But, I really enjoyed it.
Aw, thank you. Thank you very much.